Hello. Today I have a big challenge. I would like to show you the famous result of the special theory of relativity, that is the formula E equal c squared, mc squared. I think that more or less everybody in the world knows this famous formula. It is the icon of the special theory of relativity, and it is definitely a milestone in the development of the modern physics. It is deeply linked to the name of Albert Einstein, and it is what we want to show, what we want to find out today. So, as we have seen in the previous lectures, the most important factor in what we have seen is just the Lorentz factor, that is the square root of 1 minus v squared over c squared. All the transformations of space and time are obtained using this factor here. For instance, you remember that the time interval, the proper time interval, passing when you are on board or on a moving spaceship, going away from the Earth, for instance, it is expressed in this way. So you have to multiply the terrestrial time, the terrestrial time interval delta t, times the square root of 1 minus v squared over c squared. So we can guess now that the same factor can be used to derive the equation of the energy of a body. Okay, so let's start with this simple consideration. As many of you know, the kinetic energy that normally is indicated with the letter T of a classical body moving at a certain speed v, it is equal to 1/2 mv squared, where m is the mass of the body and v is the speed, the velocity. Okay? So this cannot be true in special relativity because this formula here does not consider the fact that there is a limit, a speed limit. So we could, for instance, here calculate the kinetic energy of a body moving with a speed 10 times the velocity of light. That is impossible, no? That is impossible to have in any inertial reference frame. So we have to substitute this formula with another expression for the energy, okay? But we have to consider the fact that this formula here should be right when we go to the limit for the velocity much less than speed of light. In this situation here, we should find that this formula here is quite correct. So let's work with these ingredients to find out a solution. Oh, first of all, we have to say that this is the kinetic energy of the body, so we must assume that classically the energy of a certain body should be the so-called rest energy when the body is still. This is the body, okay, standing still, plus the kinetic energy due to the fact that the body is moving with the velocity v. Okay, so the formula that we must find in the classical limit is just this one. Okay, let me write it in this corner. Energy classic is equal to rest energy plus 1/2 mv squared. Okay. Now let's work on the relativistic energy, assuming that the relativistic energy E is equal to the rest energy divided by the Lorentz factor. Why do I guess this? Why do I start with this hypothesis? Well, because the energy of the body must increase when the speed increases. So, if I put this factor at the denominator here, as you can see, when v equals 0, okay, when v equals 0, this is 1 minus 0 divided c squared is 0, so 1 minus 0 is 0, square root of 1 is 1, so we get that the energy becomes exactly the rest energy when the body is not moving. And this is correct. On the other side, I see that increasing the velocity, this number decreases, but as it is at the denominator, the result is that the energy increases. So this seems to be a good deal. Let's see what happens in the classical approximation. So first of all, we have to remember that the square root of a certain number, in in this case, let's do properly. The square root of 1 minus v square over c square is equal to write 1 minus v square over c square elevated to 1/2. This is a well-known property of the square root. The reason is simple, because you can, I can show you that if you have square root of, let's say, a times square root of a, by definition this is equal to a, and if you substitute at the symbol square root the exponent 1/2, when you multiply two numbers with the same basis, you add the exponent, so 1/2 plus 1/2 is equal to 1, so you find the same result. So this is the exponential way to represent the square root. But we also know that when the square root is at the denominator, so you have to evaluate 1 over square root of this, you simply write a minus sign in front of the exponent. This is due again to the fact that if you have 1 over a times a, this is equal to 1, and this is obtained in the exponential form. If you substitute to this expression this one, you add the exponents. This is minus 1, this is plus 1, that is a elevated to 0, that by definition is equal to 1. So this is the right way to express in mathematical form this stuff here. So let me write that this is equal to E0 times 1 minus v square over c square to the minus 1/2. Now, before going on, I need to remind you some properties of a binomial expression elevated to a certain exponent. Let's start with this case. Suppose that you have 1 plus x to the second square. You know that this is equal to 1 plus 2x plus x squared. You remember is the square of the first plus the double product plus the square of the second. If you have a minus sign, this becomes a minus sign, and the last term stays with the plus sign. Now 1 plus or minus x cubed. You know that is 1 plus or minus the 3 times the first squared, that is 1, times the second, then it is plus 3 times the first times the second squared minus, plus or minus x cubed. Okay. I could continue, but what happens if x is small? In the approximation of x much less than 1, so when the second term in the binomial expression is much smaller than the first one, here you have a number that is much smaller than 1 squared. You can neglect it because this term here is much smaller than this one. For instance, suppose that x equal 0.01. When you square it, this becomes 0.0001. That is definitely much smaller than 2x. Okay? What about the cube? Here, obviously, you can neglect this, and you can neglect this as well when compared to this term here. Okay, you could say, yes, but also this term is much smaller than 1, and the same for this. But if I cancel this as well, I have a trivial expression that this stuff here is almost 1. I know that it's almost 1, but I need to maintain some information related to the second term. So I have to maintain at least the first element. So it's easy to show that continuing, if I've got this elevated to a number n, this will be equal to 1 plus or minus n times x plus all the other smaller terms. You see, you can deduce this by the fact that here, when you have the square, you put a 2 in front of the linear term. Here, the 3, and so on. So the general expression is this one. But it is easy to show that this is valid not only for integer numbers, but is valid also for fraction numbers, positive, negative numbers, real numbers in general. So what I can do is the following. As we know that in the classical approximation that we won't find as a correspondent to this classical term. In the classical approximation, we have that v square over c square is much smaller than 1. Okay, so I can use this formula here applied to the expression of the energy. So the energy becomes more or less the rest energy times 1. So I have to take the exponent n and put it in front of the x term. X is v square over c square in this case. The sign is minus, so it is minus what? Minus 1/2, so it becomes plus 1/2 v square over c square. Okay? Well, now I simply, this is in the classical approximation. Huh? So in the classical approximation, if I distribute, I've got E0 times 1, E0, plus 1/2 E0 over c square v square. Okay? Classical. Now we are ready to consider this expression looking at this. What do you see? You have that E classical is equal E0, okay, plus one term that is 1/2 E0 over c square v square. But from these two expressions, we find out double frame. It's too important. We find that E0, the rest energy, over c square equal m. This E0 is equal mc square. And this is the fundamental equation for the energy found by Albert Einstein. It is important to comment this immediately, otherwise we lose the meaning of the equation. Let's go back to this. If I substitute to the energy this expression here, I've got that energy is equal to mc square over square root of 1 minus v square over c square. Many times, often, when talking about the theory of relativity, some people say that when a body is moving at a very high velocity, very close to the speed of light, the mass of the body increases. This is misleading. I don't think it's the correct way to interpret this equation, because the mass of the body is m, and it doesn't change when you change the velocity of the body. What the thing that happens is the energy changes with this formula here, and the result is that the energy increases due to the fact that you have this factor here at the denominator. The way people, what people mean when they say the mass increases is that they call the rest mass m0, and then they say that you could write this expression here like this: E equal mc square full stop, where m is equal m0 divided the square root of 1 minus the square over c square. I mean, it is not wrong mathematically, but it is it is hard to think that what really changes when the body is moving with a certain velocity away from me is its mass. Its mass is constant. What changes is the energy. Because the mass is intended as the quantity of matter. So the quantity of matter is the same. The inertial mass is this one, is m0. Okay? And if you write the question in this way, the general equation of the energy for in special relativity, it is clear that you have to assume that the mass varies in this way. But I think it's more correct to use this one, full stop. Okay? Well, E0 is mc squared, where m is in m0 if you want. Okay. So normally when people say write the equation E equals mc squared, they intend that this is the rest energy of a body of mass m0. Okay. This is for sure correct, written in this way. Anyway, you can play with the question as you want. The important thing is to remember that if you write that heat 0 is equal m0 c squared, then the energy of the moving body is this. Okay, full stop. Good. To conclude this session, I would like to show, but this right immediate, to say that if you have if you are on board of a spaceship moving fast, very near, very close to the speed of light, the energy associated with the spaceship moving, as measured by the Earth, is very, very high, because this number tends to be near to zero, so the energy tends to become infinite when you are reaching the speed of light. So that means that if you want to increase the speed of the spaceship more and more, you need an incredible high amount of fuel, of energy, to continue to accelerate, because in a certain sense, using this misleading picture, but efficient in some way, it is like it is as if the mass of the body, the inertial mass, increases with this formula here, so it becomes heavier and heavier, and it is very, very, very difficult and probably impossible to accelerate more and more. Okay, thank you very much.